Okay, so let us start on chapter 4 in this video. And this is going to be more or less about message integrity. Message integrity. Integrity. Okay, so what is message integrity and why are we concerned and how does it differ from secrecy? Okay, so so far we have been only so far concerning ourselves about ensuring the secrecy of the communication, right? So what about integrity? So far only cons- we are concerned with secrecy of communication, communication, right? What about integrity? What about integrity? Okay, first of all, what is the difference? We need to make sure that we have some idea of what it means by integrity, right? So one of the first major things that we care about integrity is that the message should have come from the party. Even if we have a adversary who is interfering with the channel of communication, we should have some sort of secrecy. We should have some sort of way of verifying that the messages are correct. Okay, which is to say, i.e., ensuring that a message that a received message originated from the intended party and was not modified. Mhm. The party and was not modified. Okay. Now, perfect secrecy means that okay, the person should not know. CCA secrecy means that a person should not know what the modification is, but that doesn't really help. You don't want a message to be modified in any way. Like it won't help if someone modifies something you don't know. Like suppose a message was send $10,000 to some person X, right? And someone modifies the message, and now they have for fun and changed what X was. You don't want your money going to some random person, right? So you want you want it to happen that if such a message was sent and some random modification happened, the system should flag an error saying that hey, there was some modification of the message. Okay, even so, such a thing should happen even if the attacker controls the channel. Right? And now you might be thinking that yes, this is important in that white noise and things shouldn't distort my data, and I should be able to verify if what the message was like something hasn't changed randomly. But that's just standard error correction, and that is not enough. If an attacker is attacking, standard error correction often involves repeating the message and stuff, right? If an attacker is attacking, they might change the same thing in every single message, right? In that case, standard error correction techniques are not enough. Correction techniques are not enough. What great not enough. And so we need the proper tools for to check for message authentication. And the proper tool is generally called a message authentication code, the MAC or MAC ID that you generally might be familiar with. The right tool is a message authentication code. Okay. And so how does the message authentication code work? So you have a user 1, U1, who has a message M. They have a key K. Okay. What they do is they generate a tag, which is called T, which is generally denoted MAC K of M. Okay. And the message then sent is M comma T. User 2, who's getting this message, okay, gets this message. Suppose they get the message M prime comma T prime. We don't know if it's exactly the same or not. They have access to the key K, and what they verify is that, hey, they run a verification algorithm verify K M prime comma T prime and see whether it says yes, this is a valid message. Now, if you fudge both the message and the code correctly, sure, great, you have managed to break the code. But if not, it's going to pop out a 0 and say, hey, there is something suspicious going on. You don't want that, right? In terms of a bank, for example, the message might be going to the bank. The bank should be able to verify that, okay, even if the message is coming from your saying that, oh, please transfer, is it actually created by you, or is it created by someone who's trying to impersonate you, right? So in all these cases, it's important. Now, let's be honest, you can't have perfect authentication, okay? Because you can never completely protect against impersonation messages, because if I really want, I can just get a gun, hold it to your head, and make you write the message I want, and then of course it will be authenticated that you sent it. But for all practical purposes, we don't want messages to be modified by an adversary. Okay. Another example is if you're buying something online, right? And the computer sends a cookie to you. Now the price might change. The buyer might be giving you some discount, and they might want to change the price somewhere. So maybe you're using a discount coupon for which the price is less, and they want to show the price to someone else which is higher, right? Um, this the price that is shown to you is recorded on a cookie. Now, when you pay money, the seller should be able to identify that, okay, this person had the correct price and things that I had set up before, and so I will accept this money and this price for them. Okay, and that is going to be somehow having to do. The only way to do it is verify that the cookie that you are sending it back was indeed correct, right? It's a valid cookie. You didn't change it to say that, oh, you showed me the price was this much. Okay, the cookie has to pass what do you call verification as having being sent by the website. Okay, so this is different from secrecy, right? Secrecy and integrity generally are orthogonal concerns. Secrecy and integrity are orthogonal concerns. What does it mean by orthogonal concerns? What it means is technically the phrase orthogonal generally refers to things like the xy axis. Even if you change x, it doesn't affect y, right? You can modify one without absolutely affecting the other. Okay, you can have one without the other. You can do anything with one without bothering with the other. So possible to have one without the other. Oftentimes, you might want one without the other. Sometimes you might want one without other. Okay, though most of the times you often want both. Most often both are needed. Okay, so in general you want both of them to be necessary. But for example, if a boss is sending messages to the secretary, they don't care if someone else can read the message, what is going on. Like, most of the messages are not going to be secret. It is, however, important that no random message gets thrown in. Someone doesn't randomly change the message, right? The only important thing is the message gets through. So in that case, you don't care about secrecy, you care about the integrity, right? So all encryption we have seen so far is actually not at all does not have any integrity. So encryption in general does not in general provide any integrity. Okay, and if you realize integrity is actually stronger than non-malleability. Integrity is even stronger than non-malleability. Non-malleability, and we haven't even seen a non-malleable scheme yet. So that means none of the schemes we have seen so far are going to be have any integrity, because none of them are non-malleable. All of them are malleable, so none of the schemes we have seen so far provide any integrity. Okay. So the standard integrity protocol that we are going to look at or algorithm would be the message authentication code. Authentication code, referred to as MAC, not for Macintosh. Okay, that's a completely different thing. So a message authentication code is generally 3 algorithms. A message authentication code is defined by 3 probabilistic polynomial time algorithms. So generator, MAC, and verify. Okay. Similar to our encryption algorithm, which is generator, encryption, decryption, we have generator, MAC, verify. Okay. What does generator do? It has the same role as before. Takes an input n and outputs a key. Takes as input 1 to the n, outputs k. So we are going to assume that the key length is greater than or equal to n. Okay, so even if it was gen was a what do you call pseudo random generator and it's making a key, that's perfectly fine. That's all part of gen. Okay, what does MAC do? MAC takes the input key, takes as input key k, and a message m, which is some length, I don't know, 0, 1 to the star. It could be any length, not necessarily the same length as key. Okay, and it outputs a tag t, which we are going to say t is defined to be MAC k of m. Okay. If it is deterministic, then it is written equal. Otherwise, generally, it will be written with our conventional arrow if it's non-deterministic. Okay. And what does verify do? Verify takes key k, message m, and tag t as input, as that should be a t, that looks like a b, t as input, and outputs verify m comma t is equal to b, where b is equal to 1 if verification is success, verification succeeds, succeeds, b is equal to 0 otherwise. Okay, and what should happen? We want correctness, so for all m and k, and all k output by gen. Correctness implies that the verification of m comma mac k of m should always be equal to 1. Okay, so this is the model we are using. There's only one standard model. We don't have to look at various different models. Okay, so only one standard model. Maybe in the future someone might say, hey, here's another model. I don't know, but there's a model. And what's the thread model? Well, here's the thread model. It's called the adaptive chosen message attack. Okay, and what does it exactly entail? What does such an attack entail? Well, it assumes that the attacker can induce the sender to authenticate all messages of an attacker's choice. Okay, assume the attacker can induce the sender to authenticate messages of the attacker's choice. Attacker's choice. Okay. What's the security goal? Security goal. Well, in reasonable terms, it should be essentially unforgeable, right? For all practical purposes, you should not be able to forge someone else's identity. That would be great, right? Only the original sender's message with its code should be verified, and everything else should fail. So, essential unforgeability. So, RGEABILITY. Forgeability. Okay. Which is to say that any message that the attacker sends, which he hasn't seen before, like if you send a message that a valid sender had sent before, of course he can see the tag, right? And so if I send a message, if I'm the attacker, I see that some message was sent before with some tag. I send the same message. Of course, it's going to go through. The tag and the message is the same. But if I send a different message, there should be a tag with that message. And if I am sending a different message with whatever tag I made up for it, it should not go through. So attacker should be unable to forge a valid tag on any message not previously authenticated by the sender. Okay. So In terms of an image, it's going to look like this. Uh, you have the receiver, which I'll call U2, and this is a person adversary. Okay. Um. Okay. So let me say initially there's a person U1. Okay. They have the key. They are going to send T1, which is Mac KM1. T2 is equal to Mac KM2, and so on. Ti is equal to Mac KMI. Okay, and all of these messages get sent. M1 T1 dot 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 MI TI. Okay, and since the user is sending all of these are going to be verified. Okay, now the adversary can see all these messages. Okay, they can see that, oh, these messages are getting authenticated, and he sends a message, he or she send a message M prime T prime. Okay, the user 2 also has the code K. Now what does verify M prime comma T prime do? It should only verify it if it is one of the messages M1T1 to MITI that was originally sent. If it's something else, it should fail. It should not succeed, not even with probability half, it should fail. Okay, so let us formally define this. Formal definition. Fix a comma pi. So in this case, pi is not an encryption scheme, but a message authentication code scheme. Define randomized experiment. Experiment. Forge a pi of n as follows. In the first step, a uniform key is generated by 1 to the n, by generator using 1 to the n. A interacts with Oracle Mac K. Let M be the set of messages submitted to the Oracle. Submitted to this Oracle. Okay. So M is a set of messages that I have submitted to the Oracle. Okay. This is important. A outputs M comma T. Okay. 4. A succeeds and the experiment evaluates 1, and the experiment evaluates to 1 if verify K of M comma T is equal to 1 and M was not something that was fed to the Oracle. Okay. All the messages that are fed to the Oracle, there is a known code, right? We only want to know that if from the code can the person forge another message. And so what is the security definition? Pi is secure if for all PBDA attackers A, there is a negligible function epsilon. There is a negligible function epsilon such that the probability of the experiment succeeding A pi of n is equal to 1 is smaller than or equal to epsilon of n. Okay? Well, that is my definition. Question, is the definition too strong? Is this something that we're talking about in the air? Is this too much to worry about? Is this definition too strong? Well, the thing is, well, maybe it sounds too strong. It's not something that's unreasonably strong. Because we don't want to know, we don't want to make any assumptions on what all the so we don't want to make any assumptions about what the sender might authenticate. We also don't want any assumptions about what forgeries are meaningful. Make any assumptions about what are meaningful. Okay, so in that case, if I don't really know what all information the person has that they're trying to get authenticated, and what we would classify that no, this is an allowed forgery, like this is fine if it's only this much, we don't know. In that case, this is the best estimate that we can make. So in a way, any max satisfying this definition can be used anywhere. So this is the best case scenario, but this is also more or less a good enough thing. Unless we have a very relaxed assumptions about very specific things, this is what we are going to look for. So a max satisfying this definition can be used anywhere integrity is needed. Anywhere integrity is needed. We don't need to change the definition of our scheme for everything. We can just use this for things. Okay. One thing to note is this system does not include note. Replay attacks are not prevented. Attacks are not prevented. Okay. In fact, no stateless mechanism can prevent this. Stateless mechanism can prevent this. Okay, and why is this true? Well, if a message and the code are authenticated, well, verify should always use that code, right? That tag should always work for the message because it has already been authenticated once. So if you send the same message and the same tag again, of course it's going to work. And that is a real life concern. So they're often actually a significant concern. So replay attacks are a significant real world concern, but our our definition cannot handle that right now. We need an even higher level of security. Okay, and we will look at that later. Maybe not in the course. Let's see. So, need to protect against replay attacks at higher level. And what to do with such attacks depends on the application. Decision about what to do, about what to do with a replayed attack is replayed message, not attack. Message is application dependent. Okay, so often you just note that this message message and tag has been used before. If you see it again, you say, okay, this is the second time, and you keep it in a state for the message, which is going to take a lot, which is why it's something that's not generally done just with the Mac system. Okay, and yeah, so for now let's stop here. Next time we'll talk about fixed length Macs and constructions. Okay.